Good morning, sir. I am Anushka Roy from Electronics and Communication Engineering Department, third year. My roll number is 34900323004. Today, I am going to discuss about pulse-coded modulation, a topic of digital communication. Think of PCM as a way of turning an analog signal like someone's voice or music into a digital form that can be stored or sent over a communication channel. Here, pulse coded modulation basically is a technique used to digitally represent an analog signal. In PCM, the analog signal is sampled at regular intervals and each sample is quantized to the nearest value within a finite set of digital steps. These quantized values are then encoded into a binary format for transmission or storage. The real advantage of PCM is its reliability. Because the signal is now in digital form, it's far less affected by noise and interference compared to analog. That's why it's used in things like CDs, telephony, and most modern audio and communication system. This is the basic block diagram of the pulse-coded modulation system, which is divided into two main sections, the transmitter and the receiver. On the transmitter side, we start with the sampler, which takes regular snapshots of the incoming analog signal. The quantizer then converts each sample into the nearest allowed value from a fixed set of levels. Next comes the encoder, which assigns a unique binary code to each quantized value. The binary data can now be transmitted or stored. On the other side, the receiver side, the process is reversed. The decoder takes the incoming binary data and converts it back into quantized values. These values pass through a holding circuit which keeps each sample steady until the next one arrives. Finally, a low-pass filter smooths out the signal, reconstructing it into a close approximating of the original analog waveform. So, in short, this chain of block ensures that an analog signal can be converted into digital form, transmitted reliably, and then recovered back to analog form with minimal distortion. So, here are the fundamental steps in PCM: sampling, quantization, and encoder. What is sampling? According to the sampling theorem, a signal band limited to FM Hz, meaning it has no frequency components higher than FM, can be perfectly reconstructed from its sampling if the sampling rate Fs is at least twice Fm. After sampling, the next step is quantization. Quantization is the process of converting a sampled analog signal into a discrete signal by assigning each sample to the nearest value from a finite set of amplitude level. We divide the amplitude range into quantization levels and each separated by a step size. The continuous amplitude values are mapped to the nearest discrete representation level. Now, we have already discussed sampling and quantization, so let's focus on the encoder. The encoder converts each quantized sample into its corresponding binary code for digital transmission or storage. Each quantization level is mapped to a unique binary code. If there are L quantization level and number of bits needed is n log L, if each sample uses n bits and the sampling frequency is Fs, then the bit rate is given by Rb equal to n into Fs bits per second. In PCM, the word size simply means how many bits we use to represent each sample. More bits mean more possible values, so the digital version of the signal can follow the original analog shape more closely. For example, an 8-bit system can represent 256 values, while a 16-bit can represent over 65,000 values, which is why high quality audio uses higher word size. Of course, there are trade-offs. Higher word size improves sound quality but also increases file size and the amount of data we need to transmit. Then there's quantization error. This is the small difference between the real analog value and the closest quantized value. The fewer levels we have, the bigger this error gets. And finally, PCM bandwidth. This is simply represents the range of frequencies necessary for its transmission. It depends on how often we sample the signal and how many bits we use for each sample. The formula is very straightforward. Bandwidth equals word size multiplied by sampling rate. Here, SQNR or signal to quantization noise ratio is basically a measure of how strong our signal is compared to the noise introduced during quantization. The higher the SQNR, the cleaner the output signal will be. To find SQNR, we take the ratio of signal power to noise power. The signal power depends on the original waveform, while the noise power comes from the quantization process. In a uniform quantizer, this noise can be calculated mathematically, and it turns out to be related to the step size between quantization levels. Now, here's the important takeaway. The number of bytes we use per sample has a direct impact on SQNR. If we increase the number of bytes, we get more quantization levels. The step size gets smaller and the noise reduces, which means the SQNR improves. We often express SQNR in decibels, and you can see from the formula here, each additional bit increases SQNR by about 6 dB. That's why higher bit depths in audio or video systems give much better quality. PCM is not perfect. Just like any communication system, it's affected by different types of noise. For example, if we don't sample fast enough, we get aliasing noise, where different signals start looking the same. During quantization, we get quantization noise because we are rounding the actual values. While sending the data, the channel can add its own channel noise, and sometimes pulses overlap, causing intersymbol interference. The drawback is that PCM treats every sample equally. Even if consecutive samples are almost identical, it still encodes and transmits all of them. This creates unnecessary redundancy and waste bandwidth. In speech signal, this is even more noticeable because the values are often very similar from one sample to the next. Oversampling can help us meet the Nyquist's criterion, but it also increases the number of samples we need to transmit, so we end up using more bandwidth. Thank you, sir.